So in your notes packet, if you guys can flip to page 2. Page 2. All right. So hopefully from that lab, that's why I kind of wanted you to look at for sure question number 6. If I see any issues with that, we'll spend a couple more, minutes tomorrow talking about the properties. But the properties were obviously one way that we could decide what the type was. The other way was the one that we've already had experience with, where if we look at the formula, we're looking for the metal. So that's not going away. This is just talking about a couple of the details for today. We're going to briefly write some notes about metallic. We're not going to do much with it, okay? But then we're going to move into ionic compounds, and I want you guys to be able to draw out that electron transfer, okay? So, should not take us too long, and then we will be done, okay? So stay with me. All right, so we got to see when we were first going over that chart on the front about who remembers, what did we say for metallic bonding? What was important? What was the one thing I told you guys to remember? If you have to look at your first page real quick to see, what did we write above metallic bonding? Anybody got it? Sea of electrons. The sea of electrons. You guys remember that was where all the electrons they're delocalized, meaning they're not staying with their little nucleus. They're kind of bouncing around. Okay, they're playing hot potato. All right, so metallic bond is what forms between a metal and another metal. Okay? Metals hold their electrons very loose or loosely. Okay? Valence electrons are allowed to flow in a sea of electrons. So again, the fancy word is that they're delocalized. And this is why metals are good conductors. Okay? So these are metallic compounds. These can be any metal out there. Be alloys, which is where we have a mixture of metals. And that's what we're dealing with the metallic bonding. Okay? Are there any questions over what I wrote down? We're all good. Okay. So the next topic is about the ionic compound. So it should already be filled in for you, so just kind of read along with me. It says an ionic bond forms between a metal and a nonmetal, which means it has a positive thing and a negative thing. So, who remembers what did we call the positive ion? Yeah, that's okay. You guys don't remember. That's okay. So if you look on if you flip it over, you don't have to turn any page. If you just flip it over, I gave you guys a little hint. So this is good to study later. Cations are your positive ones. Anions are your negative ones. Okay? So I'm just going to write that right above this little positive and negative so that I know when I look at this later. Okay? All right. In an ionic bond, electrons are going to be transferred from the metal, the positive guy, the cation, to the nonmetal, or the anion. Okay? Metals are going to lose electrons to form positive ions. Nonmetals gain electrons to form negative ions. A positive and a negative are going to attract each other. All right? So there's that idea that positive and negative are going to attract, just like magnets that we kind of talked about earlier. Okay? Excuse me. And an ionic compound can also be called a salt. We wrote that on the front page as well. When you dissolve ionic compound in water, it can conduct electricity. It's an electrolyte, right? That was the word that we put with that. Electrolyte, just like in Gatorade. Electrolyte. Okay? So, what you guys have to be able to do is show what happens during the formation of an ionic compound. So if you look at these pictures below, so I already gave you guys an example of two things. We're going to draw one in a second together. But if you look right here, I put 3s1 and I put 3s2p5. All right, so I brought in electron configuration again, okay? just to stress that we need to know the valence electron. So electron dot notation was the one where we had to go around in a circle around the letters to show the valence electrons. What are valence electrons, you guys? The electrons where? In the outer shell, right? So for something like sodium, sodium was in group 1. Group 1. So that had 1 valence electron, right? Chlorine was in group 17. So chlorine had 7 valence electrons. Okay, so that's all I was showing you with the electron configuration. If that goes over your head, please don't worry about it. All right, so what we have to do now is we had to write our electron dot notation. So if you notice, I wrote out Na for sodium, and I put 1 dot by it. Then I drew out chlorine, and I put 7 dots. 1, 2, 3, 4, 5, 6, 7. A lot of you guys are still struggling with this, by the way. On that last test, so many people struggled with that one. So we got to get it right. Can't mess that one up. All right, once you have your two things, you're looking at how they can fit together to help each other out. What was the ultimate goal in bonding? Here, you don't have to change your page, but look at my page. What is our goal for bonding? Why are we even doing this? Why do the metals and nonmetals all transfer electrons or share or anything? They're trying to get that full outer shell. They're trying to get 8 valence electrons. So, looking at this first example, sodium has to just get rid of 1. Chlorine just needs to gain 1. So we show that electron transfer by putting an arrow from that single one to the single one over here. The next step is we put sodium into brackets. If you lose one thing negative, you become 1 positive. Let me finish. Hey, listen. Okay, we get that positive 1. Chlorine, we're going to fill up now. So he has 8, but because he gained 1, he became negative. Then we count up how many of each we have. 1 and 1, right? Write down the resulting ions and number of each. Sodium and chlorine pushed together 1 of each. So tomorrow coming in, we're going to do this one for the warm-up. Okay? Or we're going to do, calcium chloride for the warm-up. All right? So please be ready to use your notes. If you did not turn in your lab, you need to bring it absolutely done tomorrow. Okay? All right. Bye, you guys. Yes, hold on one second.